Hi everyone, and thanks for the introduction. It's a pleasure to be here, and let me also thank the organizers. I think it's a great initiative for all students. So today I'll be talking about an old topic of research, which has seen a bit of a revival in the past decade. It's called quantum thermal machines. And as the audience is diverse, I'll try to keep the talk at an introductory level. If there are questions, please feel free to interrupt me. And before I start, let me mention that this is a very diverse field of with literature from many different areas of physics. So this introduction is a bit biased towards the things that I work on and I find interesting. So the goal here will be just to give you a flavor of the field rather than a tutorial, which would take more time, I think. So first to tell you a bit about where I work, I'm from the Department of Applied Physics at the University of Geneva. The majority of the people here are working experiments on the building in the right here, work on experiments on quantum information, cryptography, and also on biophotonics. We also have a fairly large theory group here, and we work primarily in two directions. One is quantum information. So we work on subtopics including and not restricted to quantum non-locality, information processing, cryptography. And the other direction that I mostly work on is quantum thermodynamics. As you can see from this chart, it uses tools from many different areas of physics. So in this field, we look at both fundamental questions, and a couple of nice examples from recent years are given here. We also look at the practical side of things, which is in the form of quantum thermal machines, and the topic for today. So why do we want to study quantum thermodynamics? So there are both fundamental and practical motivations for this. On the fundamental side, one of the main questions is whether you can apply thermodynamic principles for single particle scenarios or quantum systems. So does it make sense to talk about heat and power work when you just have one particle? And if you can apply these principles, what are the laws of thermodynamics that govern quantum systems? So as you know, the first and the second law here, they're derived for macroscopic systems statistically in the thermodynamic limit. So does it make sense to have something similar in a single particle scenario? So another motivation is whether you can derive these laws from basic principles of quantum mechanics, which would mean that classical thermodynamics is not a fundamental theory, but rather an emergent theory from more fundamental principles. So on the practical side, it's important to note that nanotechnologies have seen significant advances. So we are approaching, or rather we have approached a situation where quantum effects can become relevant in the operation of devices. For example, here's the IBM quantum computer here. So for example, if you have a quantum computer, one of the main limiting factors of classical computing is heat dissipation. So you'd like to have an understanding of the same thing in a quantum system. So a related question is that the thermodynamic laws that you obtain from this fundamental side, they can also sometimes give you fundamental bounds on the performance of your devices. For example, in classical physics, we have the Carnot efficiency, which is the upper bound for the efficiency of all heat engines. And we'd also like to know what effects does quantum physics have inside nanomachines. For example, what is the effect of quantum entanglement or quantum coherence in the operation? Can they give you some benefit in the operation? So let me start with the introduction to quantum thermal machines.
Hello.
So, yes.
Yeah, I just wanted to ask one small question.
Yes.
In the previous slide,
Sure.
You are using D bar Q, and so is there some nomenclature for that? I mean, is it different from the normal DQ or?
So that's because it's not a proper differential D bar Q. That's why.
Okay.
This is really just from classical thermodynamics. This is not a proper differential. This is not a correct mathematical object. That's what it reflects here.
Okay.
Yeah. So moving forward. So what what do I mean by thermal machine? A thermal machine is basically a system that is connected to thermal reservoirs, and it's designed to perform some useful function. So, for example, in classical physics, you just have you mostly deal with two situations. First, you can have a system that's connected to two thermal reservoirs at different temperatures. You allow heat to pass from the hot to the reservoir, and in the process, you can extract work. And this is nothing but a heat engine. And you can also have the opposite situation. You provide work to the system. You force heat to flow from the cold to the hot reservoir, thereby cooling the cold reservoir. And this is a refrigerator. And so depending on the task that you want to perform, you can design different kind of a thermal machine. As I said before, the laws of thermodynamics also give you fundamental bounds of operation. For example, the Carnot efficiency is given by this expression, and it upper bounds the efficiency of any reversible heat engine. So now the questions are whether you can design thermal machines with quantum systems, and whether these quantum thermal machines can give you any advantage over classical thermal machines. So the story of exploring thermodynamics with quantum systems goes back to 1958 to the work of Scovil and Schulz-DuBois. They were working on something called a maser, which is the equivalent of a laser, but it emits microwave emission and not light emission. So what this model really consists of is 3 quantum levels. So you have 1, 2, and 3. And they're coupled to a hot reservoir with a frequency filter that such that this hot reservoir can only induce transitions between 1 and 3. So effectively, this hot reservoir only couples with the first and the third levels. And similarly, we have the cold reservoir, which only induces interactions between these excitations between levels 2 and 3. And thirdly, we have the first and the second levels coupled to a resonant radiation field such that this relation is satisfied. So we have that this energy gap between 1 and 3 is minus this energy gap, the cold energy gap, is equal to the energy gap, is basically the frequency of the emitted light here. So basically, now, if you wait long enough, the system reaches thermal equilibrium, and the populations of these levels are given by the Boltzmann factor. So if you take the ratio of the populations between N1 and N2, it's described by the temperature T cold. Sorry, I think there's a mistake here. This should be 2 and 3 here, not 1 and 2. And similarly, there's 1 and 3, and it's described by the hot temperature. So you can think of this system as basically a thermal machine that has the system as a working fluid. There are thermal reservoirs, and this radiation field can act like a piston because you can extract work from it. So you can think of the energy exchange with the bus as heat, energy exchange with the field as work. So this relation here gives you directly the first law of thermodynamics. So the work is basically the same thing as the heat in a cyclical operation. So at equilibrium, for example, if you have emission or excitation from the first to the third levels, you will have de-excitations from the third to the second and second to the first. You can also have the opposite process. You can have excitation from the first to the second, second to the third, and third to the first level. So we see that there's heat flow and there's work. So we can operate this system as a heat engine. And in particular, when you have population inversion between levels 2 and 3, so the population of level 2 is greater than the population of level 3, you can operate this system as a heat engine. So you're just using the previous formulas that I gave you, you can show that N2 over N3, which is greater than 1 here, directly gives you the condition that the frequencies of the cold and the hot transitions is greater than Tc over Th. And now you can calculate the energy of this, the efficiency of this engine. So the efficiency is simply the work, which is what you get from the radiation field, over the heat that you get from the hot reservoir. And this is just 1 minus the ratio of the frequencies of the cold and the hot transitions. And from here, it's upper bounded by this expression. So you can also have the reverse operation. So if you have N2 less than N3, you can operate your system as a refrigerator. And here, if you calculate the coefficient of performance of the refrigerator, see in the paper or by yourself, it's a simple calculation. You can show that it's exactly the Carnot efficiency of a Carnot coefficient of performance of a refrigerator. So what we showed here is that the maser obeys the Carnot bound, which is basically a restatement of the second law of thermodynamics. So this was really the first time that people thought about thermodynamical laws in quantum scenarios or few level scenarios. So are there any questions till now? Okay, if not, then we move forward. So what this model did not talk about is dynamics. It did not talk about time evolution at all. So to talk about time evolution, let me take a small detour. So I'm sure all of you are familiar with closed quantum systems that are isolated from the environment. So if you have a system S that's isolated from this, and there's an insulation layer here from the environment, you know that the evolution of the system is simply is unitary. It's Hamiltonian evolution, and we know that the state of this system follows the von Neumann equation. So you just have the trace of the, or rather the commutator of the Hamiltonian and the state. But in thermodynamics, we like to describe a situation where a system is interacting with a thermal reservoir. So in general, in open quantum systems, the question is, you have a system that's interacting with some environment, and you'd like to describe the state of the system only, and not the state of the environment. So you would like to take a partial trace over the full state just to describe the system. In general, this is an extremely hard problem. But you can make some simplifying assumptions. For example, if you assume that there's weak coupling between the system and the environment, and you assume that the environment is Markovian, which means that it does not have memory. It basically means that the evolution of the system at any given point in time does not depend on the past. It only depends on the present. And under these two approximations, without going into too much detail, you can derive, So if you have weak coupling gamma between the system and the environment, you can derive the Lindblad equation. And just to tell you a bit about this equation, you can see that the first part of this equation, which is the left side, is just the von Neumann, from the von Neumann equation. It's just the unitary part of the evolution. The other part, it describes dissipation into the environment, and these are called dissipators. So this is basically one of the most popular methods to describe open quantum systems when you have weak coupling between system and environment. So this gives us a tool to describe the evolution of a system that's coupled to a thermal reservoir. And I should tell you that these operators Li, they're called jump operators, and they depend on the system that you consider. So are there any questions till now?
So what do you exactly mean by weak coupling here?
Okay, so let's move forward. So
Shishir?
The Lindblad equation gives us a nice tool to study what another pioneering work by Robert Elitsky from 1979. So in this work, he considered a general open quantum system with a time-dependent Hamiltonian that's described by a Lindblad equation that's interacting with some thermal reservoirs, and the evolution is given by the Lindblad equation. And if you calculate the average energy of the system, so you have to calculate basically the expectation value of the Hamiltonian through this equation and going to the Heisenberg picture and getting this equation. You see that the average and the change of the average energy is dependent on two parts. First is the change of the Hamiltonian, and the second is the change of the state. The change of the state coming from this equation. So what this paper did was associate this part with the work done and this part with the heat dissipated. And why does that make sense? Because in an experiment, the thing that you have control over is the Hamiltonian. For example, you change some parameters like there's a, okay. I thought there was some messages in the chat. So can
you
I don't
have
remember
any physical intuition for any physical intuition behind the structure?
So okay, about the exact form of the structure, I don't think I have the mathematical capability to explain you. But this equation is the most general evolution under the approximation of weak coupling and Markov approximation, such that the evolution that you get is both trace preserving. So if you start with density matrix trace 1, you end up with a valid density matrix trace 1. And you get completely positive evolution, which means that no matter what the situation, no matter how many other systems that your system is connected to, the matrix that you obtain here, the new matrix at time t, it'll always be positive. So I don't know if I can explain this structure more than these two things. So it's really a mathematical object in reality, although you can derive it from microscopic principles.
I see. Okay.
So any other questions?
I guess no, we can carry on.
Yeah. Okay. So basically, this gave us the tool to describe time evolution in a quantum thermal machine. So let me just talk slightly because I think it's probably better that I start the slide again. So this brings us to Robert Elitsky's pioneering work from 1979, in which he considered the Lindbladian evolution of a system that's connected to some general system that's connected to some reservoirs, and the system is described by a time-dependent Hamiltonian. Now, to calculate the average energy of this system at time t, you can go to the Heisenberg picture and get this expectation value of the Hamiltonian, the time derivative of the expectation value of the Hamiltonian. And you'll see that it consists of two parts. The first part is contains the derivative of the Hamiltonian, so the rate of change of the Hamiltonian, and the second part consists of the rate of change of the state from the Lindblad equation here. So what this work did was interpret the first thing as work and the second thing as heat. And why this makes sense? It makes sense because the Hamiltonian is something that you can change in the experiment. So you can change some parameter of your system, for example, the magnetic field, and the Hamiltonian changes. Something that you cannot directly control in an open quantum system scenario is the state. So that gives you some uncontrollable dissipation, which is the heat. So the work and the heat current are given by these two integrals. And as I said, the heat is associated with the change of state, work with the change of Hamiltonian. And this gives you a way to re-express the first law for open quantum systems. So you just have the internal energy on this side, the work, and the heat. And this equality is the first law. So what he considered next was a cyclical process operating between 2 times t equals 0 and t equals t naught, and the system operating between 2 thermal reservoirs. And the operation is cyclical. So the system Hamiltonian, which has some time-dependent part, has the time-dependent part becoming 0 at these 2 times. So you complete one full cycle. And you now you operate the system such that it operates as a heat engine. So if you calculate now the work and the heat, this equality has to hold, because in a cyclical process, the change in internal energy of the system has to be 0 because of this relation. And what he did was use the von Neumann entropy, and I'm not sure all of you are familiar with it, but those of you who've taken some courses in quantum information, he used this form of an entropy of a quantum state and used properties of the Lindblad evolution and showed that this thing holds. So the heat exchange with the first bath over the temperature of the first bath, the heat exchange with the second bath over the temperature of the second bath is always less than 0. And this should remind you of the second law of thermodynamics. So if you use 1 and 2, what you can show is that the efficiency of your heat engine, so the work that you can get and the heat that you get from the hot bath, the ratio is bounded by the Carnot efficiency. It's a very simple calculation from here and here. So this is a remarkable result because it's completely general for a quantum evolution, for an open quantum evolution in the case where you have weak coupling between the system and the environment, which is the case in a lot of actual scenarios.
I'm sorry, but can you repeat the how you got the first equation Q1 T0 plus Q2 T0?
Okay, sure. Let me go back to the previous slide. And please, if something is unclear because my flow has been completely broken by the internet, so just stop me wherever. So here we have the relations that the work is given by the trace of the state times the rate of change of the Hamiltonian. And similarly, the heat is given by the trace of the Hamiltonian times the rate of change of the state. So this is exactly what we have here, right? And the first law, the first law tells you that this equality holds. So, and this is 0 because it's a cyclical operation here. And this is why you just end up with the heat plus equals minus the work from here. So if you said this 0, so heat equals minus work. Is that okay?
Right. So we interpret Q1 as Q1 and Q2 as heat absorbed and heat emitted, something like that.
Yes.
Between the two reservoirs.
So Q1 and Q2 are the heat exchanged in 2 steps of the cycle. For example, you can take a Carnot cycle or Otto cycle, in which you connect your system to the reservoir. That's what it means.
Okay, yeah, that makes sense. Thanks.
Yeah. So any other questions till now? Okay, if not, then we'll move forward. So this is one of the most important results in the field, I think. And the papers, I should mention that the papers I've told you about until now, the one by Schulz-DuBois and the one by Elitsky, they're both really accessible papers. So if you like to read them, they're also very short. I think the one from 1958 is just 2 pages. So I highly recommend reading these 2 papers. So what we've seen till now is that when you have a quantum scenario, you can have the same laws being followed, and also the same efficiency bounds being obtained for the the operation of heat engines. So now the question is, can a quantum effect or a quantum feature of the system help you with something? So I'll give you one example of a system in which quantum entanglement can help you. And for this, I'll have to introduce you to the 3-qubit refrigerator. So as the name suggests, there are 3 qubits interacting with each other, and they're coupled with 3 different reservoirs. So one is coupled to T hot, one is coupled to T cold, and one is coupled to a room temperature reservoir. And the system is designed such that the energy transitions between these levels of the qubits follow or rather satisfy this equation. So the room temperature reservoir energy is just the difference between the energies of the hot temperature qubit, not reservoir, hot temperature qubit minus the cold temperature qubit. So I write the Hamiltonian of the 3 qubits just in the form of the excited states of the qubits, and there should be an EJ here. I'm sorry about that. And the interaction between the qubits is very specific. So it's like this. So this interaction is basically inducing the transitions between these 2 states. So you have 1 on the cold qubit, 0 on the room qubit, 1 on the hot qubit, going to 0, 1, 0. So what cooling means in this scenario is that the cold qubit goes from state 1 to state 0. That's what cooling means. So one other important detail here is that the coupling between the qubits has to be weak, because we want the eigenenergies of the 3-qubit system to be controlled by this Hamiltonian and not this Hamiltonian. It's again too much detail, but it's an important one. So something that you can note from this transition is that only 2 states are important for the evolution of the cold qubit. Only the states 0, 1 and 1, 0 of the room and hot qubits are important. So only these 2 things are relevant. So what they did in this paper is I think it was one from 2 or 3 years after this actually, but they didn't do this in the original paper, was treat them like a virtual qubit. So you have just 2 states, you can treat them as 2 levels. And it has energy you can calculate directly from here. It's it's EH minus ER. Yeah. And now let me just check. I think there's probably a mistake. No, there's no mistake. Okay, so the energy of this virtual qubit is equal to the energy of the cold qubit. And now, if you take a situation where this coupling between the qubits goes to 0, you let qubits 2 and 3 equilibrate at their respective bath temperatures, and again the populations will be given by the Boltzmann factor. So this is the population of the 0 level of the room qubit. This is the population of the 1 level of the room qubit, and same here. And as you can see, the Boltzmann factor is at temperature TR with energy ER. And again here, EH and TH. And now, if you calculate for the virtual qubits, what's the Boltzmann factor? So basically the probability of, or rather the population of this state over this state, so 0, 1, 0, 1, 1, 0, 1, 0, and you play around with some parameters, you can show that it's like an effective Boltzmann factor at an effective temperature T virtual. And this T virtual is given by this equation here. So it depends on the energies of the hot and the room qubits and also on the temperatures of the two qubits. And as it happens, if this temperature is less than the cold temperature, the cold qubit is cooled down. And why this is, you can simply see through this logic. So this interaction, if I go back, if you turn on the interaction between the qubits, it's inducing transitions between these two levels. So the cold qubit is effectively coupled to a reservoir at temperature TV. So the cold qubit is coupled to both TV and TC. So if TV is in fact less than the cold temperature, it's going to push the qubit to become even cooler. So what this basically means, if you let the system evolve into a steady state at long times, you'll find that your cold qubit reaches a thermal state that's at a temperature that's less than T cold. That's what this means. So are there any questions till now? So just let me know, because I cannot see most of you.
Can you explain the second statement, like after the equilibrate?
Sorry?
After the second equation, right up there. After the equilibrate, that this one, n upon 0 on r, that one. Yeah, this one.
So, okay, this one, or the one below. Sorry.
The above one.
Yeah.
Okay. So this is basically, this is the same thing as what we had here. Let me go back to here. So the populations of the levels, because we have a thermal reservoir, they'll always follow the Boltzmann factor. This is exactly the same thing as I have here. So this is the population of the 0 level of the room qubit. This is the population of the 1 level of the room qubit. And this is the same thing for hot qubit. Is that more or less clear? Or
Yeah, I guess we can carry on.
okay. So any other questions, just let me know. And so as I said, in the stationary state, the qubit C is a thermal state, so diagonal, at temperature T, which is Ts, which is less than Tc, S meaning the steady state. So the steady state of the system is a bit funny, because depending on the parameters of your system, it can either have entanglement or have no entanglement. So what this work here considered was, or rather investigated, is what happens when the steady state is entangled. So for this, they introduced an enhancement quantifier. So basically, this is Tc minus Ts when the state is not entangled, and sorry, when the state is entangled, and Tc minus Ts star when the state is not entangled. So if this thing is greater than 1, that means that entanglement is pushing the system towards an even cooler temperature. So Ts is less than Ts star. So what they found was that when there is entanglement in the steady state, the fridge can in fact cool your system to even lower temperatures. So here is the plot between this enhancement quantifier and a measure of entanglement, which is called concurrence. And they found that for any value of T hot, you find the same increase in this factor. So it's always greater than 1 when you have entanglement. And funnily, this cooling enhancement only depends on the entanglement. It only depends on the concurrence, and not on the hot reservoir temperature or the room reservoir temperature, which suggests a very deep relationship between entanglement and cooling. So this is really funny because cooling is a task that has an analog in classical physics. Of course, it's derived from classical physics, but entanglement has no analog in classical physics. So this was just to give you an example, or rather just one example of a system which can actually be benefited from having a quantum feature. So until now, we've considered tasks that have analogs in classical physics, that have motivation in classical physics. For example, a heat engine or a refrigerator. But what if now you have a task that is exclusively non-classical? So one such example is this system. So here I have 2 qubits that are weakly coupled to each other, and each of them is coupled to a thermal reservoir at temperature T hot and T cold, where of course T hot is greater than T cold. And the reservoirs are Markovian, and they follow the Lindblad equation. So again, you have unitary part from the von Neumann equation. You have dissipators corresponding to the interaction with the baths. And when this coupling between the 2 qubits is weak, you can show that this equation is local. So which means that this dissipator, or rather, there are 2 sets of dissipators that correspond to the hot and the cold qubits. And these exact coupling rates, and the details are not very important here, they depend on the exact statistics of your bath. For example, when you have a bosonic bath, they follow this relation. And dissipators have, of course, the same form as before, as I showed you. So what has been shown previously in different works, for example, this one from 2015, is that if you let the system evolve for a large range of parameters, you can create steady state entanglement. So you start with the non-entangled state, you connect it with 2 thermal reservoirs, and you end up in a state that's entangled, which is really a funny result, because all you did here was use thermal resources. You did not use any amount of external control or any form of any external influence. So it's attracted a bit of interest in recent years, and it has been shown that, for example, you can create maximally entangled states in the system. You can also create genuine multipartite entanglement, as done in this paper. And but I'll be focusing on some shameless advertising of my own work in this talk. So this paper. So what we did in this paper was considered an interaction of this form between the 2 qubits. So what this interaction shows you is that either you can have an excitation in qubit 1 and de-excitation in qubit 2, or de-excitation in qubit 1 and excitation in qubit 2. So this is the only kind of transitions that you can have. And when you take this form of interaction and you solve your Lindblad equation, you find that the steady state, which means that the state at a very long time, always has this form. So in the computational basis, you just have 4 probabilities and 2 coherences on these elements, on these places. And one thing that you have to note is that the presence of these coherences does not guarantee that your state is entangled. For that, you have to look at, for example, the PPT criterion, which is the positive partial transpose. Basically, what you do is you take the partial transpose of the state and determine a condition for the positivity of the state. And when you do that, you find this. And this condition tells you that your state is entangled. So whenever the modulus squared of your coherence is greater than the first and the last probabilities, your state is entangled. So showed in this in the paper that I cited before was that the coherence has a very close relationship with the heat current. And the heat current is defined this in the same way as Elitsky's paper. And using this, you can show that there's a critical amount of heat current, which means that there's a lower bound on heat current, such that you must have this amount of heat current if you have to see entanglement in the steady state. Which I think is a very cool result because, again, the heat current is really motivated from classical physics, but entanglement again has no analog in classical physics. And we showed analytically that this holds. Whenever the steady state heat current is greater than this critical value, you have an entangled state. And this is something called the negativity. It's just a measure of entanglement. The details are not so important. And this is a necessary and sufficient condition. So if you have entanglement, you always have the heat current is greater than the critical value and vice versa. So are there any questions until now about these two slides, or even before? If you think of something, just let me know. Okay, so if there are no questions, let me move forward. So let me show you this result with some plots. So on top, I have the heat current that's being shown as a function of the detuning between the qubits, and also the temperature of the hot bath. And as you can see, and on the bottom, I have the negativity of the state in both the plots as a function of the same things, the detuning between the two qubits and also the temperature of the hot bath. As you can see, as soon as the heat current value falls below the critical value, you have zero negativity. And as soon as it rises, of course, you have some negativity. And it's the same thing here. Whenever the heat current falls below zero, your state is not entangled. So in this way, you can see the heat current for the system as a weakness to the entanglement between the two qubits. And let me also mention that this is probably not an artifact of the model, because it's already a similar result has already seen has already been seen. Sorry. Is there a question or? Okay, I guess there was.
I guess someone accidentally turned on their mic.
Yeah. Okay, so this is not an artifact of the model, because it's already been seen in some other things. For example, more recently in this paper. So something that so it's nice because you can create some amount of entanglement in this 2-qubit thermal machine. But of course, you cannot directly create maximum amount of entanglement. So is this entanglement useful for anything? And can you perform a non-classical task with this this small amount of entanglement? This was discussed in a very recent paper, and I'm going to talk about it now. So one of the things that they showed was that you can teleport a quantum state and with the amount of entanglement that you create with the 2-qubit thermal machine. So teleportation, let me just briefly tell you what this is, if you don't already know. So it's basically a protocol that allows you to share quantum information using shared entanglement and some classical information. So if you have two parties, Alice and Bob, and they share an entangled state of 2 qubits, and you have a classical channel. So Alice can send some bits to Bob. She can then share a quantum state without actually sending it to Bob. So how this works is this. You just input a quantum state. Alice makes a Bell state measurement on her part of the state and also the state that you sent her. Depending on the outcome, she sends some bits to Bob, 2 bits to Bob, and Bob performs a unitary on the state that he has, depending on the bits that he obtained. And what he obtains is exactly the state that you input. So for this protocol to work absolutely perfectly, you need a maximum amount of entanglement in the state. So you need a Bell state here. But as it turns out, teleportation is achievable to some degree with non-maximal entanglement. So, so for that, I have to tell you something about the singlet fraction and also the fidelity of teleportation. What this this quantity f really tells you is that is how much the state that Bob gets in the end overlaps with the initial state that you sent to Alice. This is called the singlet fraction, and this is called the fidelity of teleportation. Fidelity is the important thing here. And as shown in, for example, this paper, this fidelity of 2/3 is achievable classically. So the state that you had, the entangled state that you had between the two parties is useful if and only if this small f is greater than 2/3, which means that this capital F singlet fraction is 1/2. This means, this basically, it's just terminology, but it means that the singlet fraction is non-trivial. So what this paper showed very recently is that with the 2-qubit thermal machine, with the amount of entanglement that you obtain, f greater than half is in fact possible. So the task that you perform here is exclusively non-classical. It's really quantum. And this shows really an operational meaning of non-classicality in a thermal machine. So I should mention that it's not the only result in this paper. They also considered Bell non-locality, and they did show a CSHS violation. And also, they also talked about quantum steering. So with this, let me give you a summary. So hopefully I gave you a flavor of the field, and we saw that quantum thermal machines can be constructed just as classical thermal machines can be constructed to perform some operations. And we also saw that quantum thermal machines can outperform classical thermal machines sometimes and perform non-classical tasks. So there are many open questions in this field because it's a very young field. But I just write 3 very broad ones. The first is the laws of thermodynamics. So you'd like to have a theory where you have a very general picture of what exactly are the laws that are being followed by an open quantum system, and not just in restrictive scenarios. And these laws of thermodynamics can help you get fundamental bounds in performance. And exactly, you can investigate the role of what's the role of quantum correlations like entanglement and coherence. And there are also, of course, a lot of open questions in experiments, and I don't think I'm qualified enough to talk about them. But I think very broadly, there are 2 questions. There's single particle control, so that you'd like to have a good amount of control over the quantum system that you use as a quantum thermal machine. And you'd also like to be able to scale this system so that you can operate it at a quantum level, but you can operate a bunch of systems collectively and get more value out of your thermal machine. So I'd like to tell you that this is a really new field. There are so many open questions, and I'd like to encourage you, if you are interested, you should definitely consider it for a specialization. With this, I'd like to thank you for your attention and invite you to read some references if you're interested.
Yeah, that's a very good talk. Thanks, Shishir. So
Thank you.
maybe I can ask audience if they have any questions at this point. Any comments or question? So I really found this talk very casual and easy to grasp at the same time. And yeah, it was very good actually.
So if there are any questions, just you can ask away or just write to me, or I'm sure Shashwat can share my email.
Yeah. Just let us know if you have any questions. Send it to our email ID qtpitalks@gmail.com in case you have any questions. We'll forward it to the speaker. So I guess thanks, Shishir.
So thank you very much. Thanks everyone for your attention and time.
Yeah.
Okay.